So we're going to break this into 5 different topics: circuits, conductors, resistivity and resistance, circuit diagrams, and then devices that you would use to measure electricity. And we'll talk about all these in detail. So let's go fast. Our first topic are circuits, and it's interesting. I don't call these electric circuits, I call them electric circles, because circuits are circular. So keep that in mind. If you look here, this is called a schematic. An electric circuit is just a path that charge follows, and in order for that to work, it must be unbroken. So you need to have a complete circle, and we use 3 different parts for a circle. You have a battery, which is drawn with a long line and a short line, positive and negative terminal. You have a conductor, and there's a switch here. By the way, this is open, so you don't have a continuous path. And then you have some device that converts energy, a light bulb. So if I were to close this switch, so I'll close it. So now we just imagine that switch is closed. It goes down and snaps shut. Now we have a path. So you have electricity coming from the positive terminal, goes up all the way around through the conductor, which is copper wire in most cases, through the light bulb, and then back home. So I have a full circle. Again, 3 elements. You have a voltage source, a conductor, and some device to convert energy. That's called a load. Historically, or really from a physics standpoint or a chemistry standpoint, we usually say that the charges that move from one atom to another are negative charges. So it's the flow of electrons, or the movement of electrons from one atom to another. They're said to be delocalized, they can jump. But in this course, we're not going to use negative charges. We're going to say that positive charges move. So if I go back to this, if I put a proton right there, since I have a positive plate and this proton will move in that direction. And if you look, this is the conventional current flow. It's the movement of positive charge, and we do not consider the electron flow. So current is always from positive to negative, and it goes against what we know that negative charge are the movers. So we will again stick with positive charge as being the one that moves, or the brand of charge that moves. Current, by definition, is simply the movement of charge. So just imagine I have a charge moving, and I'll draw, I don't know, a wire. The movement of positive charge within that wire past some point in space, maybe past some line, is the definition of current. So while the actual current is the flow of electrons from the negative terminal to the positive terminal, we use the convention current to model electric circuits. Again, that's positive charge moving. Conventional current is the flow of positive charges flowing from positive to the negative terminal. And going forward, we'll use the conventional current when we discuss electric circuits, and it's the opposite of the actual flow of charge, or the opposite of the flow of electrons. The definition of electric current is that, and I'll put this into words, current is how much charge moves past or through some point in a wire, past a location, per unit time. So current is I, charge is Q, just like our study from electrostatics, and time is T. And the units for this are, or the units for current are amps, which we'll define in a second, which are coulombs per second. So we'll abbreviate that. Q is the amount of charge, T is the amount of time, and so on. So let's apply this after we restate what the units are. So amps, or amperes, often called amps, are the units for electric current. So electric current is measured in amps. Sometimes you'll see it written as AMPS. Other times you'll just see an A. Other times you'll see coulombs per second. So that's amps.